Hi, I'm Sean Reagan, and today me and my partner Santiago are going to tell you a little bit about our project, which is on big vehicular data analysis. So today we're going to talk about what is big data and what that has to do with vehicular networks, some facts behind both big data and vehicles, the motivation behind collecting big vehicular data, and how it can be useful. We're going to talk about the different types of vehicular data, what a vehicular network is, and then the architecture for how big data can influence vehicular networks. There's then Santiago's will be talking about the data analysis process, VanNet simulations, results and analysis, as well as the conclusion. So, in general, big data, according to the National Institute of Standards and Technology, or NIST, are extensive data sets that primarily have the characteristics of volume, variability, and velocity. It requires that these data sets are scalable to allow for efficient storage, efficient manipulation of data, and easy analysis. Now, data analysis is the process of essentially extracting information from these big data sets. It involves choosing the proper data set, preparing the data, which might be some pre-processing to the data, maybe to format it for the particular use case that you're trying to analyze, and then applying models. The point of these models is essentially to extract features from the data and classify the data as different things. And then from these we can identify key findings and generate a report, which is basically just a summary of the data as well as some graphs and stuff like that. And then we have vehicular networks, which is ultimately the communication between the vehicles and the cloud. And then put them all together and we have big data vehicular networks, or big data vehicular data analysis. So the American National Security Agency says that on average about 1,800 petabytes of data is being processed every day. And this is growing at a rapid pace. By 2020, the new information generated per second will be 1.7 megabytes for every human. It's estimated that by 2020 there will be around 250 million connected cars. And today in Florida we have over 14 million drivers and more than 1,000 car crashes every day. So almost 90 people on average every day lose their lives to a car crash, and more than 250 people are injured every hour from a car crash. So given some of those facts, now dig into the motivations behind big vehicular data. So essentially the motivation in general behind big data is to find patterns and customer preferences. In our case, that's really driver preferences as well as driver patterns or traffic patterns. This can help prevent car accidents, improve the general traffic flow, improve GPS accuracy, as well as help create intelligent transportation systems, or ITGs. So we have different types of vehicular data, and this is just a few of them. General traffic data, so this might just be, this is just the flow of traffic and maybe how things like a stop sign or street lights help affect traffic. There's sensors in vehicles. There's already tons of sensors within vehicles, such as speed sensors, mileage, temperature sensors, ambient light sensors, etc., that we can get plenty of data from. Then there's GPS data from maybe from your car's built-in navigation system, or from people using something like Google Maps on their phone. So if you think of like GPS data, Google already uses live user data to help find the quickest route. It shows people live traffic updates and congestion, and helps show people the fastest route to their destination by collecting this GPS data from all the different users in real time. Then there's road condition data, which would be things like congestion and maybe things like detours and potholes, or accidents, for example. Then there's vehicle maintenance information, which would be like how often someone does maintenance on their car, or how often certain cars have mechanical issues. Then we have vehicular networks, or VANets. These basically work off the same principles as MANETs, and MANETs are essentially like IoT devices or mobile devices, where one device can talk to another device, which can talk back to a base station. So in the case of VANets, each vehicle is a node. So there's vehicle-to-vehicle communication, vehicle-to-infrastructure communication, and vehicle-to-broadband communication. In the case of vehicle-to-vehicle communication, this is really OBU to OBU communication, where OBU is onboard unit, which would be the unit inside the car. Vehicle to infrastructure is normally referred to as OBU to RSU, RSU being roadside unit, and vehicle to broadband is the same. So now we have this image here. It's a high-level image, but a very good image of basically an overview of VANets. And we can talk about how big data helps with this situation. So you can see here we have a taxi talking to another taxi, which this taxi can then talk to this bus, back to an RSU, and back to a base station, a broadband base station. So you can see that in this case it takes multiple hops to get back to the base station. Basically two OBU to OBU hops, as well as an OBU to RSU hop, and then an RSU to base station hop. So big data in this case can be used to help improve the communication flow and improve the overall distributed network that's going on here. So we can look at some vehicular data like traffic patterns, for example. So maybe in areas with high traffic, you might need more RSUs to help with traffic congestion, and not just traffic congestion like physical road traffic, but also networking traffic, for example. So this is how big vehicular data can be applied here. It can essentially be used to help improve the overall performance of your VANet, and help you strategically choose where to place things like your RSUs, how close or how far away your RSU needs to be from a base station, and help you basically gather a coverage map of different areas, different intersections and stuff like that. And this big data can basically be used to, the VANet can be used actually to collect more big data from the cars, right? So now that you have an interconnected car network, you can actually transmit a lot more data back to a backend server for data collection. So now the cars can become a little bit more sophisticated, where maybe they know when they're driving past another car. They're becoming sort of smart cars, and this data can be gathered and transmitted back to a backend and be turned into its own sort of big data. And this is why it becomes sort of a cyclic relationship, because data collected from VANets can then be used to help improve VANets and help improve vehicles and traffic conditions in general. So, I mean, VANets aside, the big vehicular data can help traffic flow in general. Like if there's an area of traffic that's congested all the time, the big vehicular data analysis will be able to identify this, and maybe extra road infrastructure can be built to help alleviate some of that congestion. So there's multiple purposes to vehicular big data. I think some of it is very sort of now, which now in the sense that it can help right away in creating new roads and new lanes, etc. And then some of it's a bit future proof. It can be used to help build RSU infrastructure and build more base stations and improve the performance of VANETs. And eventually we're going to have this sort of connected car network. So we're going to need to analyze the data that we have now and collect more data to ensure that the performance is as good as it can get. Because something with real-time data from like a car and the amount of data that needs to be transmitted is very complicated to do. So performance is important. So now Santiago is going to talk to you a little bit about how the data analysis works and some of our simulations.
Hello everyone, I'm Santiago, and I want to start by explaining big data vehicular analysis process. The data analysis process is a pipeline, but before the process begins, we must think about how to store large amount of data, and therefore a closer design must be implemented. The recommended machines specifications are dual CPU with 8 cores and at least 88 gigabytes of RAM, and of course a lot of hard drives. The first step is collecting the data. In this case, the data comes from IoT devices, roadside units, police officers, computers, and other sources. The next step is the ingest the, the data into the systems. So once you have the closer set up, we have to decide how to load the data. And there are two options, batch or event-driven. Batch is for structured files such as relational databases, and event-driven is for more near real-time events like logs. Uh, After the data has been injected, our next step is staging. Here, the data is stored in a format and size that can be processed. Um, in Hadoop, the big data framework uh, that we are using for our project, the data is divided in smaller pieces to facilitate the processing step. Um, the next step is to process the data. Here is where the data is transformed from raw data to meaningful information. Here also we can reduce, sort, convert the data, uh, do machine learning, analytics, data mining, and so on. Then you can have then you have to we have to define a workflow or querying system and access control management. And finally, we obtain the insights or results that we want. All right. So next, I want to introduce you to Sumo, a traffic simulation system. It is open source and was developed by employees in the Institute of Transportation System at the German Aerospace Center. So to run the simulation, we have first to create some files. So we have two options. First, create the files manually. So we have to input all the information, all this information, which is the speed, the shape of the vehicle, the roads, the nodes, and so on. The other option is to export um, a map and then transfer and then convert that map to a Sumo file. So after I convert the oh, the map to Sumo file, um, I'm also using a random trip Python script to create a random simulation. All right, so let's see the simulation. So this is the FAU map, and I'm using 500 cars. Okay, let me put some delay here. All right. So we can observe the simulation. All right, so once the simulation is done, we can save our results in a XML file. So it looks like this. All right. So that's collecting the raw data. So this data is not easy to analyze. So we have to ingest that data into our framework. In this case, is Hadoop, and then convert that data in something that we can understand. All right, and then we we can create graphs and different analysis in that data. All right, so after the data is processed, we can make like a deeper analysis. So we can perform data mining. Um, we can use the Weka tool to create mathematical models. Um, we are also using a data set of vehicles traffic provided by the city of Aarhus in Denmark, observed between 2 points for a set duration of time over a period of 6 months. So the raw data is 35 gigabytes, um, but the data was distributed in smaller files by a big data processing system. All right, so after the data was divided in smaller uh, sets, we used the Weka tool to create a linear regression model. So this is how our linear regression model looks. Uh, we are comparing its speed and the count of cars in between 2 points. and then we are comparing the real values with the predicted values. All right. So to conclude, uh, big vehicular data analysis is one of the most popular areas of research. Uh, can be can be extremely important for companies and organizations because it reveals information such as patterns, customer preference, and trends. It can be used to help finding patterns that can prevent or mitigate car accidents as well as traffic congestions. BA nets with big data analysis provide a lot of real-time applications. To process big data, a complex computer architecture and framework is required. We found that a Hadoop framework meet all of the requirements to process big data. After data is processed and divided and reduced, data mining tools such as Weka can be used to create mathematical models. Thank you very much.